Okay, I didn't click that button. Sorry. Now you guys see the red light or something?
Yeah.
Yeah.
So anyway, everything in the balanced chemical reaction is directly proportional. So I can say 1 mole of nitrogen is going to give me 2 moles of ammonia. Now that of course assumes that there's enough hydrogen, right? 2 moles of nitrogen would therefore give me 4 moles of ammonia. And then 0 moles of nitrogen would give me 0 moles of anything. And so here's some conversion factors put in a row here. So 1 mole of nitrogen is equal to, in other words, would require 3 moles of hydrogen. Now that's exact, isn't it? And then if I have these two enough, I will get 2 moles of ammonia, and I will make 92 kilojoules of energy. So here I've taken some of these and converted them into conversion factors so you can see what we're doing there. So then let's just solve a problem. So how many moles of ammonia can be made from 3 moles of hydrogen? So here's the balanced reaction. And how do I start the problem? I got 3 moles of hydrogen, and I need a conversion factor to get rid of moles of hydrogen and to keep moles of ammonia. So then where do I get these numbers? Directly what's in front of them on the balanced reaction. So in front of ammonia, there's a 2. In front of the hydrogen, there's a 3. So when I do that, moles of hydrogen cancels out, and I end up with 2 moles of ammonia. So then another one is how many moles of ammonia can be made from 6 moles of hydrogen. So I'm starting with 6 moles of hydrogen.
That's not important.
Notice that this is the same conversion factor. And then I did for 9 moles of hydrogen using the same conversion factor. And then what I'm really doing here is I'm generating data. Then I plotted the data. So here's the moles of hydrogen, and here's the moles of ammonia. You see it's a straight line passing through the origin, so it's a direct proportion. And the slope of the line right here is really 2 moles of ammonia for every 3 moles of hydrogen, which is exactly the conversion factor that we're reusing. So how many moles of nitrogen are needed to react with 75 moles of hydrogen? So I got 75 moles of hydrogen. I need to get rid of moles of hydrogen, keep moles of nitrogen. I get the numbers from the balanced reaction. So in front of the nitrogen, there's a 1. In front of the hydrogen, there's a 3. So I get 25 moles of nitrogen. And here's the equation for what we were really doing. So here's the slope of the line, right? We would generate data with that. So questions so far? Let me make sure that. Okay. So here's another problem. How much heat energy is given off or absorbed when 75 moles of hydrogen is used in this reaction? So heat is a product. That means it's going to be given off, right? Another word for that is evolved. The reaction container will get hot. So to do the mathematical part, you got 75 moles of hydrogen. You want to get rid of moles of hydrogen, and you want to keep kilojoules. So where do I get those actual numbers? Well, it's from the balanced chemical reaction. So in front of hydrogen is a 3. In front of kilojoules is a 92.2. Okay. So this is also a conversion factor. Okay. So questions so far? So here's an energy diagram, and I introduced this previously. So here's potential energy on the y-axis, and on the x-axis, it's not really time, but it's the conversion of reactants into products. So you can see here, the reactants have a lot of potential energy. Should get the reaction up here. Can't do it. So the reactants have a lot of potential energy compared to the products. So when you convert reactants into products, you're giving off all this energy represented by that red arrow. And for an endothermic reaction, which you have to put energy into it to make it happen, you have to heat it up or something like that, there's less potential energy in the reactants than there is into the products. So you have to supply that energy. You have to add that heat energy. Okay, so going from moles of one thing into moles of another thing is the simplest level. And the most complex level is going from grams of one thing into grams of another. So, is everything a direct proportion? Yes. But we don't want to combine direct proportions into some complex thing that we don't really understand. So right now we got two conversion factors that we're going to use. One is the stoichiometric conversion factor, and one is the molar mass. So what that means is that the atoms and molecules in here, they just react with each other like this. Well, three of these guys get together with two of those guys. They make one of those guys, three of those guys, and they give off 200 of those guys. They never think about how much they weigh. So in their world, what works is molecules and moles. So you could say 3 atoms, or you could say 3 moles of atoms, right? And all of this will work. That's their world. But in our world, we can't count atoms, we can't count moles. What do? We have to weigh things. So if our world uses grams and their world uses moles, what is the conversion factor to get from one world to the other? It's grams per mole, which is the molar mass. So in unit 3, we learned how to calculate the molar masses. Now I'm just giving them to you here for the different entities. So we'll go through these calculations. And at the same time, we're going to prove to you the law of conservation of mass. Matter of fact, what is the reason why we have to balance chemical reaction? It's really because of the law of conservation of mass. So how many grams of phosphoric acid are needed to react with 100 grams of magnesium? So we're out here in our world. We have to get into their world using the molar mass as a conversion factor. So I got 100 grams of magnesium. I need to get rid of grams, keep moles of magnesium. So I end up with getting about 4 moles of magnesium. So I went from here into their world. Now the question is, if I have 4 moles of magnesium, how many moles of phosphoric acid do I need? So now I have to use the stoichiometric conversion factor. So I want to get rid of moles of magnesium, keep moles of phosphoric acid, and to get my answer is moles of phosphoric acid. So where do I get these numbers? Directly from the balanced reaction. So there's a 2 in front of phosphoric acid, a 3 in front of magnesium. So I get 2.7 moles. That means that to react with 100 grams of magnesium, I need 2.7 moles of phosphoric acid. But we're not done yet because the question is asking for how many grams of phosphoric acid. So we went from here into their world, and then we went from magnesium into phosphoric acid. Now we have to come back out and convert that moles into grams. So here I did that using the molar mass for phosphoric acid, and here's the answer. So here's what we figured out so far. For every 100 grams of magnesium requires 268.8 grams of phosphoric acid to react with. That means that on the reactant side, we have 368.8 grams. When it's all converted into products, we should have 368 grams of products because of the law of conservation of mass. So I'm going to just calculate this and this and this just to see that we know how to do this. So how many grams of magnesium phosphate are made from 100 grams of magnesium? So I'm out here, 100 grams of magnesium, I have to convert into moles. Moles of magnesium then has to be converted into moles of magnesium phosphate. Then I have to turn moles of magnesium phosphate into grams of magnesium phosphate. So I did that. So here's grams of magnesium into moles of magnesium, and then into, wait, am I doing that right? No, down here. Moles of magnesium, and then into moles of magnesium phosphate, and then finally into grams of magnesium phosphate. That's where I calculated that number right there. Okay. Then, what about for hydrogen? I need to calculate this number. So I converted, I'll just show you this way. So I went from 100 grams of magnesium to moles of magnesium, from moles of magnesium into moles of hydrogen, and then back out into our world into grams of hydrogen. And I got 8.31 grams of hydrogen. So if I add these two up over here, I get 368.7 grams. So now, do you believe in the law of conservation of mass? 368.8 turns into 368.7. Well, what do you know about uncertainty? This is plus or minus 0.1. This is plus or minus 0.1. These, in fact, are the same number. I can't tell that they're different. So we disproved the law of conservation of mass. And do chemical reactions obey the law of conservation of energy? The answer is yes. If I look at all the energy over here and all the energy over here, the only way to make that equal right here is to add 200 kilocalories over here. Okay. So we can do a problem. How much energy would be given off if 100 grams of magnesium were consumed? So I would do the problem like this. 100 grams of magnesium into moles of magnesium, from moles of magnesium into kilocalories. Okay. That's how I got to 274. Okay. So does that make sense to everybody?
Yeah.
I like that. Thumbs up. Okay. Okay, I'm going to stop screen sharing for a minute because there is a oh, come on. Sorry, still trying to figure this out. What was I trying to do? Participants. Why is it not showing that now? There's a better view, but I can't find it right this second. Anyway, so back to screen sharing. Okay, so another level of difficulty that I'm going to show you, but I'm not going to actually make you do it. It's called limiting reactant problems. And really all you do is you simply have to consider how much of more than one reactant. So you essentially have to do the calculations twice. Okay, but I'm not going to actually do that, but I'll show you what it's like. So how many grams of nitric acid can be made from 100 grams of nitrogen dioxide, 25 grams of water, and excess oxygen? When we were doing problems in the previous part of this chapter, we were assuming that there was enough of anything you needed. Here, you can't assume that. So they're saying that you can make a certain amount of nitric acid with 100 grams of nitrogen dioxide and a certain amount from 25 grams of water. So let's look at the two calculations. What if I used up all of the water? So I got 100 grams of water. I'm out here. I got to convert into moles of water, and from moles of water into moles of nitric acid, and then back into grams of nitric acid. So I got 1.39 moles of water, gives me 2.77 moles of nitric acid, which then gives me 175 grams of nitric acid. So what that means is, if I use up all 25 grams of the water, and there's enough of everything else I need, I can make 175 grams of nitric acid. Let's do the other calculation. If we used up all of the nitrogen dioxide, so I got 100 grams of nitrogen dioxide, turn that into moles, turn moles of nitrogen dioxide into moles of nitric acid, and then back into grams of nitric acid. So I got 2.7 moles of nitric acid, 2.17 moles, nitrogen dioxide, 2.17 moles of nitric acid. Turn that into grams, I can make 137 grams. So now the answer is, how much can I make? Can I make 175? Or can I make only 137? The answer is you can only make 137, because after that you don't have any more nitrogen dioxide. So nitrogen dioxide is the limiting reactant. So if you ever take Chemistry 161, 162, they can ask you questions like, okay, well, how much water was left over? And if you have a way to keep track of all your calculations, then you can do that with those kind of calculations. But to me, I just want you to get the basics. So here's another important calculation, and that's the percent yield. So the percent yield for a chemical reaction is the grams of product that you actually get from the experiment divided by the theoretical yield that you calculate. Everything that we calculated is theoretical. So what if you actually do the experiment? Then you would get the actual grams of the product that you actually get. So in the above problem, the theoretical yield was 137 grams of nitric acid. What is the percent yield if you only got 102? So the percent yield is you got 102 out of the theoretically 137 grams possible. That gives you a 74.5% yield. So why would you get less than 100% yield? So one is you didn't allow enough time for the reaction to go to completion. And I see that quite often. I used to teach organic chemistry labs, and students like, well, if we hurry up and get out of here, I can get out in the water and go surfing. So they're rushing everything, and they don't allow time to go for the reaction to go to completion. Another possibility, looking at this example right here, you need 1 part of A for every 1 part of B. What if you throw them together and you don't mix them? A has to come into contact with B, otherwise you will not have the reaction. Like if you tried to bake a cake and you never mixed it, it wouldn't be a very good cake, would it? Also, another reason you wouldn't get 100% yield is because you have impure reactants. What if you weighed out 100 grams of A and A was only 90% pure? Well, you didn't weigh out 100 grams of A. You weighed out only 90 grams of A. And then there could be side reactions. So we're thinking A plus B gives you C, but what if another reaction is possible? 2A plus B gives you a different product. Another major one is the reaction is reversible. There's an equilibrium. In Unit 5, we talk about equilibrium quite a bit. So we're thinking A plus B goes to C, and now C is going to stay there forever. But that's not necessarily the case. Oftentimes, reversible reactions, C will convert right back into A and B. That means that you never have the reaction go to completion. The rate in going in this direction then becomes equal to the rate going in that directions, and none of the concentrations are 0. Another possibility is that the temperature was too low to overcome the activation energy. So almost every process I can think of has an energy barrier right here. If you look at a big boulder on top of a cliff, it's going to fall down, but it's not falling down, is it? It has to have something to overcome its stationary effect of its momentum. Okay? Frictional coefficient. And the same thing goes with, pushing a car that's out of gas or anything else like that. It's hard to get it going, but once you get it going, it's easier. So same thing with a chemical reaction. That's why if you have a can of gasoline, it doesn't automatically just explode. You have to throw a match on it, you have to heat it up, you have to do something to get some of the molecules up over that barrier right there. And because gasoline is an exothermic reaction, it gives off this heat right here. As soon as some molecules go over here and give off some heat, that heat is now used to take the rest of the molecules and get them over that energy barrier. Another possibility is that you have an endothermic reaction, which means that you have to constantly put energy into it because there's less potential energy in the reactants than there is in the products. So if you don't heat it up or do something to supply that energy, the reaction won't happen. And then having a sloppy chemist is not a good answer because, as we know, chemists are the best, right? Yeah. So questions so far?
No.
Okay. Now this is in a red box. I'm not going to put this on the exam, but it's kind of like a warning for you, okay? So gas volumes and pressures can also be used in stoichiometry problems. So look at this problem. How many liters of hydrogen are required to make 20 liters of ammonia? Now, if you're not even paying attention, you might go, oh, 20 liters of ammonia, I got to get rid of ammonia, keep hydrogen, and then there's my answer right there. But why is it we can treat liters just like we did moles? Well, you have to understand the gas laws. And so the gas law is PV equals nRT. And so we're going to have a whole chapter on this. So what I did is I solved for the volume over here, this algebraically. So I get this right here. And then if all these gases, if the nitrogen, hydrogen, and ammonia are all in the same container, that means they're at the same temperature. That means they're at the same pressure. So these right here are constants. And R is already a constant. So when we do this, we see that the volume is now equal to the moles times this constant right here. In other words, the volume is directly proportional to the number of moles. That's why we can treat it just like moles right there. Anyway, I'm not going to give you that kind of problems. I just want you to realize that you may come across those on a standardized exam, and I don't want you to be taken by it. So here's a summary of everything that we did. So yeah, this is rocket science. So here's a form of liquid rocket fuel. Hydrazine, 1 mole of hydrazine reacts with 2 moles of hydrogen peroxide, and you give off 1 mole of nitrogen gas, 4 moles of water vapor, and you give off a bunch of heat. Okay. So let's think about this rocket that we're looking at right here. Why is this showing up like that? What is coming out of the rocket right there? Anybody know?
Explosions.
But here's the chemical reaction right here. What's the product of that chemical reaction? What's coming out right here? Nitrogen and water vapor, right? And why is it glowing like this? What if I took a mixture of nitrogen and water, gas, and I heated them up really, really hot? What would they do? They'd give off atomic emission. Remember that from the previous chapters? So 2 things are happening here. The chemical reaction is producing nitrogen and water vapor. It's being thrust this way because of the expanding gases because of this heat right here. So that heat is expanding the gases. The heat's causing the gases to glow, and it's causing this rocket to propel forward. In other words, the rocket is pushing off of these molecules right here to get forward motion. Does that make sense to you? What I'm trying to get you to do is realize that all the things that you're learning in chemistry are directly applicable to the world that you live in, the world that you look at. So anyway, I did some more calculations over here, so you got some more examples. And then, oh yeah. So I found that picture one time, and I had to use it, okay? So you look at the cat, he's not like really, really happy right here, but then when are cats ever really happy? So this picture is really good for everybody. Because if you like cats, you'll go, well, look at that cute little kitty. He has the opportunity of a lifetime. He gets to go into space. And if you don't like cats, it's like, oh, good. That's a great way to get rid of cats. Get it? Anyway. And here I put a review of basically everything that we've learned about chemical reactions. So completing the reaction, what type of reaction is it, exothermic and endothermic reactions, how many grams, and then I showed you how we need to calculate molar masses from unit 3. Here's some stoichiometry, more stoichiometry. Yeah. So anyway, that's a good review, I think. And at the end of unit 3, I showed you that we had these conversion factors going from grams of something into moles of something and back and forth, right? That's the molar mass. We went from moles of something into molecules or atoms or formula units of something using Avogadro's number. And we had learned how to go from moles of something into moles of one of the elements. In other words, using the chemical formula. Those were the 3 conversion factors that we had at the end of unit 3. Now, we just learned another one, stoichiometry. So now we have 4 tools in our toolbox. And just to show you where it ends, this one we'll get from chapter 15. It's not a very important one. And this one we'll get from chapter 17. It's extremely important. And that's it. So for the 4th and 5th exams, this is all you got. That's 6 tools in your toolbox. That's it. Oh, yeah. Hold on, I have a visual. So I love Bob the Builder. He's a real role model for kids nowadays. But I found this on the website one time. So this guy, I guess a carpenter, spent all this time organizing his van because he's got all these tools and everything. So you can see that he's got quick access to all his tools. But then how many tools do you have? Only 6. If you were a carpenter and you walked onto the job site with only 6 tools in your toolbox, they'd laugh you off the job site. So even Bob the Builder has more tools than you guys got. But Bob the Builder, he's my hero because he solves problems. He doesn't create problems, he solves problems. And then these guys. Did you guys watch Teletubbies when you were younger? Or maybe you still do, I don't know. And it's okay, not judging. But they don't know how to solve anything. They always need somebody else to come in and solve their problem. So they're, I think, a very bad influence on children, where Bob the Builder is a good influence. So finally I found this on the web, and it just kind of shows you that Teletubbies really are a bad influence on our children. See that? Anyway. Okay. So here's my visual, Bob the Builder. I don't remember exactly why, but he's in the lab here with me. So anybody have any questions about that chapter?
Negative.
It's a short chapter, an easy chapter. I made a video on it. And now we'll get to another chapter. This is also kind of short. And, I'm a biochemist. I'm not just a regular chemist. And to me, I think about attractions for everything. There's been a lot of drugs that are produced that work really well when you take that drug and you put it right on its target protein. It kills that protein off, could cure cancer, it could do anything. But now that you take that drug and you inject it into a person's bloodstream, or you have them eat it, hopefully that will get into the bloodstream that way. The problem is it doesn't get to where it's supposed to go. It doesn't get to the target protein. The reason is because of the attractive forces. So if you take water and oil, they don't mix, right? So what if this drug is soluble in oil? Is oil soluble in the bloodstream? No, it's not. So what makes a drug effective is it cannot go through all the different places it has to go and end up ultimately getting to that target protein or that target DNA or whatever it is the target is. So we've already studied intramolecular attractions. Those are simply the bonds, right? So bonds are very strong compared to the intermolecular attractions. That's what happens between molecules. So here's the strength of some bonds. So you see single covalent bonds. The nuclei are attracted to two bonding electrons. So the bonds are long. They're kind of easy to break, at least easier to break. Double bonds, the two atoms are attracted to four bonding electrons. So they're shorter and stronger. Triple bonds between six, even shorter and stronger. And ionic bonds are kind of all over the place. So they can be extremely high. Okay. In contrast, the intermolecular attractions are not bonds. And some of them are extremely weak. So we have four categories. Londons is very weak. Dipolar are weak. Hydrogen bonding a little bit stronger. And ion to dipole, maybe stronger, but I don't have any values for that. And I do gotta warn you, if you go online, you'll find all kinds of different terminologies. Myself, I used the term van der Waals forces wrongly for many, many years. Anyway. So a polar molecule behaves like a magnet. And a magnet is attracted to other magnets. So a nonpolar molecule, like a piece of aluminum, doesn't act like a magnet, and this will never experience strong intermolecular attractive forces. So if I take a polar molecule, which has a dipole in it, you guys know about this. Di means two, so two poles, a partial positive and a partial negative. If I bring a positive charge up to this, for example, a sodium ion, there's going to be attraction to this side and repulsion to this side. If I take that same positive charge and hold it up to a nonpolar molecule, there's nothing. Okay. So we'll look at them in terms of the weakest first. So London's dispersive forces is the weakest. So these are the only attractive forces that a nonpolar molecule will ever experience. So here's two symmetrical molecules or atoms on a collision course. You can see that their electron clouds are perfectly symmetrical. When they slam into each other, and I've been trying to get a way to visualize this, I made it so that this one completely won the collision and this one completely lost the collision. That's not exactly true. But these electron clouds right here repel one another. So as they bang into each other, This one in red completely lost. Its electron cloud was way deformed over here. So here I have a whole bunch of electron cloud with not enough positive charge to neutralize it. So this is a partial negative side. This is a partial positive side because it's so close to the nucleus. So that partial positive is going to be attracted to what? The electron clouds of the other. So I wish I had these balloons. Just haven't had a chance to go get them. If you take two round balloons and you smash them into each other, they both deform each other's electron clouds. And when you let go of them, they just simply bounce apart again, just like nothing happened. But during that collision where their electron clouds are deformed, you get this attractive force, which is called London's attractions. So for 1 fraction of a second, those two things are attracted to each other. Okay? And they bounce apart like nothing happened. Do electrons actually collide into electrons? The answer is no. Do electrons ever experience friction? The answer is no. So therefore, during this collision, the clouds may deform, but no energy is lost. We call it a totally elastic collision. No energy is lost. And we'll talk about this in the chapter on gas laws. If I got a container and I got, say, a pressure of 2 atmospheres in that container, and I don't heat it up, I don't cool it down, I just don't do anything to it. If I come back in 1,000,000 years, there's still going to be 2 atmospheres of pressure in that container. And the gas particles are colliding all the time, but they don't lose any energy. So London's forces occur between all molecules. So they're not important to a polar molecule because polar molecules have more powerful attractions. But if you're a non-polar molecule, this is the only attractive force you will ever experience. That's why it's important. And even though these are weak, I kind of use the Menehune concept. 1 Menehune may not be strong, but what if you got 1,000,000 of them? And they turned out to be quite significant. So here's something I pulled from organic chemistry. Here's 2 molecules that have the same molar mass, the same type of molecule. The only thing that's different between them is that this one is rather spherical, it's tetrahedral, and this one is rather linear. So if I look at the boiling points, this one right here boils at 9.5 degrees. This one boils at 36 degrees. Same mass, same type of molecule. What is the difference? It's called van der Waals contact, is what describes how we get the London's attractions. Spherical molecules can only interact in only a short surface area, whereas linear molecules have the whole length here that they can interact. So this turns out to be a stronger attraction than this. So here's fat molecules. Here's fat, and here's an oil. Now the working definitions for a fat versus an oil is that a fat is a solid at room temperature, whereas an oil is a liquid at room temperature. So you talk about vegetable oils, right? They're mostly unsaturated triglycerides. And fat molecules are solids that are mostly saturated fatty acids. And these are not showing up very well. I don't know why. This one shows up okay. So here's a molecule of glycerol. This is glycerol up here, glycerol up here. So if I hydrolyze this oil, I'll cut right there, right there, right there, and what I get is glycerol and fatty acids, which I can make into soap. Anyway, they're the same kind of molecule. The difference is that in unsaturated fatty acids, like this one right here, you have these double bonds. See that? And double bonds in nature are almost always in the cis configuration. What that means, if you take the two carbon atoms that are in the double bond, one thing goes off that way and another thing goes off that way. They're not showing you the hydrogens right now. So where this is tetrahedral, this is planar trigonal, and this is planar trigonal. So when you introduce an unsaturated double bond into a fatty acid, it causes it to simply change direction. Okay. So these fatty acid tails are simply all over the place, whereas you look at for fatty acids, saturated fatty acids, they're all straight and linear. So this one is getting more and more round looking, and this ones are keeping more and more linear. So we have this situation. So here's unsaturated fatty acids, here's saturated fatty acids. And that's enough to explain why oils are liquid and fats are solids. So, questions about London's attractions? Okay. And the next one is dipole to dipole attractions, or dipolar attractions. So, as the name implies, it occurs only between polar molecules. That's molecules with permanent dipoles. So here's an example. Here's hydrogen chloride. If you look up the difference electronegativity, it's 0.96, which meaning that is a polar covalent bond. So this is a polar molecule, isn't it? So here's the dipole in one. Here's the dipole in another one. Notice that this would be repulsion. However, if I flip this one around, then I see that partial negatives are lined up with partial positive. Now that becomes an attractive force. So repulsion and attraction are both possible. But which one is stronger? You could consider this love and this hate. So what is stronger, love or hate? Hopefully somebody will say love, or at least people are thinking that, right? Here's another way to think about it. Say I have a bunch of magnets and I throw them in a box. Magnets could either be in the repulsive configuration or the attractive configuration. So I take a bunch of magnets, I put it in a box, and I just shake the box up like this, and I throw the box across the room, so I'm not going to influence what happens. And I go and look at in the box, what am I going to find? Are all the magnets all stuck together? Or are they all repelled by one another? They're all stuck together, aren't they? So the attractive forces are way more important in the real world than the repulsive forces. Let's go back and think about oil and water. They don't mix. Most people will tell you, oh, they repel one another. But what I'm telling you is that it's the attractive forces that predominate here, and they're wrong. Why water and oil don't mix is because the attractive forces between water molecules are so strong that they repel or push out the nonpolar molecules. Nonpolar molecules got nowhere else to go. So everything in nature really can be explained with the concept of attraction being way more important than repulsion. Then the third one is hydrogen bonds. So hydrogen bonds, first of all, are not bonds. And if I had my way, I would be able to go through all the literature and all the textbooks and get rid of that word bond, and we'll just say hydrogen attractions, okay? All they are is very strong dipolar attractions. So they have to meet a certain criteria. And the criteria is that the partial positive charge has to be large and the partial negative charge has to be large. That makes sense? And so if you look at electronegativity, what it really means is that the positive charge derives from a hydrogen bonded to one of the three most electronegative elements, and that are fluorine, oxygen, and nitrogen, okay, which spells fun, if you remember, right? So the hydrogen provides the large partial positive because, unlike any other element, hydrogen has only one valence electron. If you start to pull away that one valence electron, what's underneath is simply the nucleus, the proton. Any other element, if you start to pull that one valence electron away from it, there's still other valence electrons and other electrons cruising around the nucleus to protect it. So one molecule has to supply the very large partial positive. That's the F, O, or an N bonded to the hydrogen. So you're pulling those electrons away from the hydrogen, leaving the large partial positive charge. And then where does the large partial negative charge come from? One of the F, the O, or the N. So in other words, both molecules in the hydrogen bond have to have some form of fun. Okay. So I should point out, if you really looked at the electronegativity values on the periodic table, you would find that chlorine has a higher electronegativity than nitrogen. Chlorine is 3.16, nitrogen is 3.04. So why don't we use chlorine? It's because electronegativity is just one measurement. It's not the whole thing. It's just an indicator. In fact, what's the important thing here is the charge density. So let's compare the fluoride ion to the chloride ion. So fluorine is in period 2, chlorine is in period 3. They're in different shells. So what that means is that the electrons giving the negative charge for chlorine are in a higher shell than for fluorine. So if you look at the surface area that -1 charge is divided by, is much greater in chlorine. Anyway, just another aspect. So here's some examples of attractive forces and the physical properties that we get. So ice contains water molecules, and every water molecule has about 4 hydrogen bonds. So that means that if you're just held by your feet and by your arms like this, you can't move around. You can't move from point A to point B. You can vibrate in place unless you're at 0 degrees Kelvin, but you can't move from point A to point B. That's why you're a solid. And so here's a picture of this water molecule right here being in 1, 2, 3, 4 hydrogen bonds. Now, how do I know this is a hydrogen bond? So here's the OH in one molecule, right? Meeting that criteria for the large partial positive. What do I need in the other molecule? An F, an O, or an N. and then there's the O. So that's a hydrogen bond. On this end, this is another hydrogen bond. Here's the OH in one molecule. Here's the O in the other molecule. Here's the OH in one molecule. Here's the O in the other molecule. So you can see this will be in the solid state. Now, when you heat ice up, it starts to melt. When you get into water, liquid water, every water molecule has about 2 hydrogen bonds. So you're not totally independent, but you can move around. It's kind of like square dancing. If you watch them do square dancing is a weird thing, but I was traumatized by square dancing when I was a kid. Commonwealth of Big Island. Everybody thought they were cowboys back then. Anyway, when you get to the gaseous state, the gas particles are moving independent of one another because they're going so fast. So there's 0 hydrogen bonds in the gaseous state. So anyway, here's the 4 hydrogen bonds in ice. And what you see is that you have a void created. I don't know if you've ever done this before, but if you take a glass and fill it up with water and put it into the freezer, oftentimes that glass will break. When water freezes it, it expands. I can give you many, many examples of that happening. Why is that? Say you're this molecule right here, and you're bouncing all around because you're just vibrating in place because you're not at 0 degrees Kelvin. But if you're moving slowly, this attractive force right here is going to capture you. Does that make sense? And the lowest amount of energy is when these attractive forces are perfectly lined up. That's the lowest amount of energy. Now, what happens if you start to increase the temperature? If you start to increase the temperature, these guys are bouncing around more and more and more. They're able to break those attractive forces, so this water molecule could end up inside this void. So what happens to the volume of ice when you melt it? The volume goes down because these water molecules can start to occupy those voids. Does that make sense to you? Why does ice float on water? So you take a certain mass of water. You look at its volume. Then you freeze it. You got the same mass, but its volume goes up. So look what happens over here. Here's the equation for density. The mass stays the same, but if I increase the volume, the density goes down. It's because of these holes right here that form when you freeze water that the density goes down. That's why ice floats on water. So why does ice float on water? Because of the hydrogen bonding properties. Almost every other substance, if you freeze it, the solid is more dense than the liquid, and then the solid will simply go to the bottom of the liquid. But with water, it does the opposite. Can you imagine what the world would look like if water behaved like most other substances? What would happen to lakes in the winter? All the ice would go down to the bottom, and then it would never thaw out again. It'd be a totally different world that we'd live in. If we were living, which we probably wouldn't be. Oh yeah, and here's another one. So here's a water molecule over here forming a hydrogen bond with that water molecule. But then here's an ammonia molecule. This is also a polar molecule, isn't it? So here's the partial negative on the non-bioelectron pair. Here's the partial positive over here. So that partial positive is going to be attracted to that partial negative is going to be attracted to that partial positive. So is this London's forces? Yes, all molecules experience London's forces. Is it dipole to dipole attractions? Yes. Here's a dipole, here's a dipole. Doesn't meet the criteria to be called a hydrogen bond. Here's the OH of 1. What do I need in the other molecule? An F, an O, or an N, and there's the N. So that is a hydrogen bond. So why does ammonia dissolve in water? Well, because it forms hydrogen bonds with water. Here's another example. So dichlorofluoromethane is a polar molecule because it has polar bonds and because it's asymmetrical. Here it is. It's volatile, which means that it evaporates quite rapidly. This is freon, also known as refrigerant. So it's a liquid that dissolves in polar solvents, but it evaporates rather quickly. This particular one is known as R22. And if I examine all the different bonds in R22, this carbon to hydrogen, it's a non-polar bond because it's only 0.35 electronegativity difference. This carbon to chlorine at 0.61 is capable of being involved in dipolar attractions. This carbon to fluorine at 1.43 is capable of hydrogen bonding. Okay. So now, F, O, or N, right? Here's the F. Would another molecule of R22 be able to hydrogen bond with another R22? They're both polar. They both have fluorine. But the answer is there a hydrogen bond there? This is a non-polar bond, so no. If this molecule has an F, the other molecule would have to have an FH, an OH, or an NH. So pure R22, what attractive forces are possible between it? London's forces and dipolar attractions, not hydrogen bonding. And this is important in the way that freons work. And I wish I had a different way to explain this, with a screen, a blackboard or something. If you look at an air conditioner, what it does is it takes the gases, and on one side of it, it compresses the gases, and it basically liquefies the gases. So what happens when you take a gas and you compress it? Well, the temperature goes up. So what the fan does, after it turns into the compressed stage, it blows air across that and it pushes the hot air outside of the room. And then the liquid freon comes into another part, and then it's allowed to expand. So what happens to the temperature when you allow a gas to expand? The temperature decreases. It's like if you were to take a gas, not a gas, you could say a gas container or a dive tank or an oxygen tank, you just open up the valve, you see the valve get cold right away. So then you let it expand over there, then you blow cold air into the room. So the balance of attractive forces is extremely strong right here, or extremely important. If I were to put water molecules in here, I would get hydrogen bonding between water and this fluorine right here. And guess what? It wouldn't work. Your air conditioner wouldn't work. So anyway, R22 has been replaced with R134A. Here's the ozone depletion potential. You can see it's almost zero for 134. The global warming potential is a little bit lower, and the atmospheric lifetime, though, is a little bit higher. Okay. Anyway, so what does this mean right here? 1300 global warming potential. It has a global warming potential 1,300 times more powerful than carbon dioxide. That's why we have to be very careful about letting this stuff into the atmosphere. Very strong greenhouse gas, and it also destroys the ozone. So, anybody else have any questions so far? Yeah. Pangolin. Xena the Warrior Princess. One of my favorite surf spots on the North Shore. Back to the lab. Sorry, I just took a short vacation there. Okay, what about the last one, which is the strongest? Ion dipole attractions. So this occurs between a polar molecule, which is the dipole, and an ion. These are stronger than hydrogen bonds because this is a full charge being attracted to a partial charge. And hydrogen bonding is just partial charges. And dipolar attractions is partial charges. And London's attractions is no charges. So these are strong. And we can use this to explain a lot of different things. So why does sodium chloride dissolve in water? The melting point of sodium chloride is about 801 degrees, which means that it's really hard to separate the sodium from the chloride. It's really hard to break that ionic bond. It's strong. But yet you can take sodium chloride and it instantly and easily dissolves in water, even cold water. So some people would say, oh, water must be a strong solvent. But then again, I want you to start thinking like how I think. It's all about attractive forces. So here's the attractive forces. The sodium ion is attracted to a whole sphere of water molecules. So that positive charge on the ion is attracting the partial negative of all these water molecules. We call this a sphere of hydration. Now, what's on the surface of this sphere of hydration is a whole bunch of partial positive charges, but then it's going to attract another layer of water molecules, so a second sphere of hydration. So you get sphere on top of sphere on top of sphere, and at the same time, the charge density keeps getting smaller and smaller. And what happens to the chloride? The same exact thing, except the charges are opposite. So that partial positive of all the water molecules is attracted to the negative charge on the chloride ion. On the surface of this hydration sphere is the partial negative sticking out. So you get another layer of water molecules, another layer of the same thing. So eventually, the attractive forces between the water and the chlorine and the water and the sodium become much more powerful than the attractive force between the bare sodium and the bare chloride together. Does that make sense? So again, it's about attractive forces. So here's a review: how to determine if a molecule is polar, how to draw attractive forces. We've learned how to do that. The only thing that we're doing differently now in this chapter is in which way are these molecules attracted to each other. So I have several examples here. Draw the strongest attraction between ammonia, here I gave you the structure, and hydrogen fluoride. So here's the partial positive. Here's the partial negative of the other one. Okay. I could also put the partial negative of the fluoride over here, right? But in either case, here's an FH. What do I need in the other molecule? An F, an O, or an N. There's the N, so that's a hydrogen bond. Oh yeah, I did draw the other one. Okay. So does hydrogen fluoride dissolve in water? The answer is yes, very strongly, because they're attracted to each other by multiple hydrogen bonds. What about between acetone and water? Okay. So here's acetone. I know you guys don't know the structure of that. You look at all these carbon hydrogens, those are all nonpolar. The only polar bond in here is between the carbon and the oxygen. Okay. So here I put the dipole accordingly. So you recall how to do that, right? The difference in electronegativity between carbon and oxygen is greater than 0.5 and less than 1.7. So I put charges on it. Same with water. So here's a hydrogen bond. Okay, here's the OH and here's the O in the other one. And here's the carbon being attracted. Wait, carbon. Carbon is not one of the criteria for a hydrogen bond. So this is a dipole being attracted to another dipole, but it doesn't meet the criteria of being a hydrogen bond. Oh wait, let me go back. So does acetone dissolve in water? And the answer is yes, because of hydrogen bonding. What about two molecules of acetone? Does acetone dissolve in acetone? Well, obviously. So here's the dipole in one, here's the dipole in the other. So what are the attractive forces between two molecules of acetone? Well, London's, because that's between anything, and a dipole to dipole, but doesn't meet the criteria for a hydrogen bond. The answer is no. So here's between acetone and acetaldehyde. So you don't know the structure of acetaldehyde, so I gave you the structure. Nonpolar, 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 nonpolar. Here's the only polar covalent bond right there. So that partial positive is being attracted to that partial negative. So they're attracted to each other by Londons, by dipole-dipole, but they don't meet the criteria to be a hydrogen bond. What about between acetone and acetic acid? So here's acetone, and I gave you the structure for acetic acid. Remember, if I take that hydrogen off, it becomes acetate. So here's a dipole here, and a dipole here, and the rest is nonpolar. So here's the partial positive being attracted to that partial negative. Is this a hydrogen bond? Here's the oxygen in one molecule. What I need in the other molecule? An FH, an OH, or an NH. Well, here's my OH. So that's a hydrogen bond. So questions so far? How do I even know you're there? It's not the first time I've been caught talking to myself. So here's a bunch of examples of two molecules and what attractions are possible between them. So here's a dipole and a dipole, a dipole and a dipole, but here's the OH, but there's no F or O and N over here. So here's an ion in a dipole. So here's the FH and an O over here, so that's hydrogen bond. This is hydrogen bond. SH, no hydrogen bond there. So this is a non-polar molecule. The bonds are only 0.48. So here's something interesting. Water is actually half the mass of dihydrogen sulfide. Yet water is a liquid at room temperature, and dihydrogen sulfide is a gas at room temperature. So what is the difference in their behavior? Attractive forces. What is the attraction between the hydrogen sulfide and water? Here's a polar molecule and a non-polar molecule, so it's simply London's. That's the only attractive force that a non-polar molecule will ever experience. So here's an ion to a dipole. Here's an ion to a non-polar molecule. What is the attractive force? Simply London's. So here's two molecules of acetone. They're attracted by London's forces and dipolar attractions. That's why acetone dissolves in acetone. Here, acetone dissolves in water. Now here you have some experience with acetone because acetone is fingernail polish remover. It's what we use to take surfboards off, wax off of surfboards sometimes. So say I squirt a puddle of acetone over here and a puddle of water over here. Which one is going to evaporate more quickly?
The water?
No. Trying to find the best way to show all you people. That's this way. No, acetone evaporates very, very quickly. It's fingernail polish remover. And why is that? Because it has only dipolar attractions. It doesn't have hydrogen bonds like water does. Now, if I took those two puddles and I mixed them together physically, would they dissolve in each other? And the answer is yes, because they're held together by hydrogen bonds. Okay, does that make sense? And just one last thing. This is an ion and this is an ion. What is the attractive force between those? Well, that's an ionic bond. That's an intramolecular attraction, not an intermolecular attraction. So anyway, attractive forces partially explain solubility. So here's water with its hydrogen bonds. Here's oil with its London's attractions. And here's air only with the London's attractions. So what's the difference between air and oil? There's a demarcation there. It's totally on the basis of mass. Oil molecules are way heavier than air molecules. That's the difference. And again, why is air and oil excluded from water? Because the attractive forces within the water are so strong that they force the other ones out. So attractive forces partially explain the physical state of matter. And the physical state of a substance is really determined by at least 4 factors. And I put first the nature of the substance, polar versus non-polar. I put it first. Okay. That's modified by temperature, because if we look at kinetic theory, if I increase the temperature, I'm increasing the kinetic energy, I'm increasing the velocity. So if the particles are moving fast, it's much more difficult to be captured by attractive forces. Then also in this equation right here is mass. So a large molar mass is going to make for a smaller velocity, harder to break away to say, for example, go into the gaseous state because you're simply heavier and you're not moving as fast. So here's something kind of interesting. All of these substances right here are nonpolar. They're all carbon-carbon bonds, carbon-hydrogen bonds. So methane is a gas, right? Gasoline is a liquid that evaporates very quickly. For example, octane, 8 carbons in a row. So this is much heavier than this, right? All London's forces is the only attractive force. And oil is a liquid that does not readily evaporate. For example, ecosane. Again, quite a bit heavier than gasoline, way heavier than methane. And then tar and bitumen and pitch are names for solids with very high molecular weight hydrocarbons and polymers, and it's often called asphalt. So if I take tar or bitumen or pitch and I heat it up, I melt it, I mix little rocks in it, put it over the ground and let it cool down, then it's called asphalt.
Is that what the roads are made?
Exactly, that's what roads are made out of. So if you ever do go to school again, you'll be using gasoline to burn. You're using oil to lubricate all your parts, and you'll be driving on asphalt. All nonpolar molecules. And finally, pressure is important for gases, because if you look at the ideal gas law right here, look at pressure. Right there is predominant, right in the front of there. Okay. So I can take methane and increase the pressure, turn it into a liquid, even into a solid. So then here's some really, really good jokes, right? I just love this one. It was so stupid. And then get it? That's a polar bear, so he's going to dissolve. So here's chemical attractions right here. And then here's human attractions. Get it? No. Pretty bad, yeah? Okay. So I made a video on the chapter on stoichiometry. It's up there. And I think I have the YouTube videos all straightened out. I hope. Anyway, the only way I know for certain is I go into my wife's account, and then I go, using my wife's account, I go look at my YouTube channel. Everything seems to be in place. Anyway. So anybody have any questions about anything?
No.
No, negative.
You're always so negative. You should be positive. Wait, that's like a dipole, isn't it? Okay, so I guess we'll do this again on Wednesday. And I have all the homework up and most of the quizzes up. So hopefully you'll get started on Unit 4 right away. Where we got some catching up to do, but we'll be okay. Okay, well, email me if you have any more questions about anything.
Okay.
All right. Thank you, Professor.
Take care now.
Okay, thank you.
Be
Thank
safe.
you.
Don't exhale, don't inhale. Okay, see you.
Bye. Thank you.
Thank you.